How about we do an example problem for chapter 25? This is 25.1, so end of chapter problems in your textbook. So this one says that the electric field strength is 20,000 newtons per coulomb inside a parallel plate capacitor with a 1 millimeter spacing. That spacing means the distance between the two plates of a capacitor. So it says that an electron is released from rest at the negative plate. What is the electron's speed when it reaches the positive plate? So the first thing we want to do, of course, is make a sketch of the situation. This is a very important skill to do to solve problems in physics and engineering. So I strongly encourage you to always try to do a sketch, put all the information that you have in the statement of the problem, put it in your picture of the problem. So parallel plate capacitor looks like this. Those are the two plates. We have a distance between the plates of 1 millimeter, so that's 10 to the minus 3 meters. We're going to put a negative charge on the left plate, a positive charge on the right plate. The problem says that the electric field inside the capacitor is 20,000 newtons per coulomb, so that's 2 times 10 to the 4 newtons per coulomb. And we're going to have an electron that is initially at rest on the negative plate. That electron is going to move to the right, and the reason why it's going to move is because the electric field is going to put a force on the electron. So there will be an electric force, F sub E. Remember that for a negative charge, the force is opposite in direction to the direction of the electric field. So since the electric field is going to the left, the electron is going to be pushed to the right. Problem says that the electron is starting at rest, so we have an initial velocity of 0 for this electron. And that's the part that says at rest. The electron is going to arrive at the positive plate, and they're asking us about the speed of the electron when it reaches the positive plate. So we're going to call that the final velocity. All right, so you have two possibilities to solve this problem. First one is to use Newton's second law. Clearly there is a force. We can find the mass of an electron. That's a number that you can look up. So we can have an acceleration calculation here, knowing the acceleration of the electron, and we have a distance, an initial velocity. It's a kinematics problem after you find the acceleration. So this is the first approach. So second approach is to use conservation of energy. Those are the two possibilities. So let's start with the first one. I'll show you both. So with the first approach, we're going to start with F equals ma. The force acting on the electron is the electric force, which is the charge times the electric field. Force equals mass times acceleration, so that gives us the acceleration is QE divided by m. We know the electric field, we know the mass of an electron because we can look it up, even if it's not given in the problem. We can find out also what's the charge of an electron, and that allows us to calculate the acceleration. Then we can plug in the acceleration in the kinematics equation, Vf squared equals V initial squared plus 2a delta x. We have delta x, we have the acceleration, we can solve for the final velocity. So solving for final velocity, we just have to take the square root on both sides, and we get the answer should be 2 times q times e divided by m times 10 to the minus 3 meters, because that's the distance that the electron is going to travel. So the mass of an electron, if you look it up, you'll find that is 9.11 times 10 to the minus 31 kilograms. The charge of an electron is 1.6 times 10 to the minus 12 coulombs. So we can plug in all those numbers. Q is E, the fundamental charge. And the electric field, we have it. And we plug in the numbers, take the square root, and your answer is 2.65 times 10 to the 6 meters per second. All right. Now let's take a look at how would you solve this using conservation of energy. So with conservation of energy, what you're doing is, well, first of all, you make sure that there is conservation of energy. So in this problem, there should be energy conservation because the electric force is a conservative force. There is no dissipation here. There is no air drag or anything like that they're talking about. So the default is there is no air drag. So this should be, in this problem, we should be able to use conservation of energy. So the approach for conservation of energy involves evaluating the initial energy. So the electron on the negative plate would have an initial energy, which is given by its kinetic energy plus its potential energy. The initial kinetic energy is 0 because it says that the electron is starting at rest. The final energy, that is when the electron arrives to the positive plate, is going to have some kinetic final and some final potential energy. And conservation of energy tells us that those two energies, initial and final, should be equal to each other. So the initial is just the initial potential, because there's no kinetic at the beginning. The final energy is kinetic final plus potential final. That's not a V, that's a U. Let me correct that real quick. U final, all right? So that's the conservation of energy equation. Now, we have an expression in the previous video. We saw that the potential energy of a charge inside a capacitor, it's a linear function of the distance measured from the negative plate. So in this equation, S is a distance measured from the negative plate. So the potential energy as a function of S is equal to the potential energy on the negative plate plus the charge of the object that we're talking about, in this case the electron, times the electric field inside the capacitor times S. And so replacing that, the charge of the electron is minus E. We can plug that in there. And we have, so to evaluate, we're ready basically to evaluate the conservation of energy. That says U initial equals K final plus U final. So what is the initial potential energy? Is the potential energy of the electron evaluated at S equals 0. So if you put that in your equation, S equals 0, that is the same as what we call the potential energy on the negative plate. The final potential energy, again, that looks like a V, but I meant it as a U. So let me UF. So the final potential energy is the potential energy evaluated at S equal 10 to the minus 3 meters, because that's the distance between the plates. So I'm just going to call it S for now. We'll replace later. So it's U minus, or U on the negative plate, minus E times S. So we can plug in U minus for initial energy, potential energy, and the U final, plug it in there. So we get that. Notice that the U minus cancels on both sides of the equal sign. And we have an expression for the final kinetic energy, which should be equal to the charge of the electron times the electric field times the distance between the plates. So replacing the equation for kinetic energy, which is 1/2 of the mass times the velocity, we get 1/2 of mv final square equals E charge of an electron times E times S. And solving for the final velocity, we get 2 times E times S divided by m. So replace the numbers, and we got, obviously we get the same answer that we got before, which is 2.65 times 10 to the 6 meters per second. All right, that's an example using the idea of conservation of energy and also electric field, force on a charge, etc. All right, see you in the next one.